Synthesis, reactions. How would you carry out the following synthesis using ether reactions? So that's a big thing that's given to us, is that it's an ether reaction. Now remember, ethers, epoxides, okay, same kind of functional group. So you can use either of those two over here. So looking at this reaction right now, I have an alkane, okay, on the left side as my starting material, and I have an alcohol plus an ether on the right hand side, okay. And so the relationship between the alcohol and the ether is a 1-2 relationship, which means they're next to each other, okay. So the only way we have learned how to make this alcohol and ether next to each other like this is from epoxides, okay. So which means that, and that's where the ether reaction comes in. But we're not going to be stopping at the ether because the alkane is our starting material, okay, not the ether. We're just taking this step by step. So this is a very good example of a retrosynthesis, okay. So I'm going to write this out as a retrosynthesis and show you how that works. So this is my product, okay, that I have. So it's 1, 2, 3, 4, 5. So that's that. And then I have the OCH3 over here, the methoxy group and the alcohol group. There is no stereochemistry here, and that's fine also, but in any case. So retrosynthesis meaning that you're writing your synthesis backward, okay. And so here, as I just said, the only way we have learned how to make an alcohol and ether right next to each other is from epoxides, okay. So which means that I need an epoxide over here. So I know how I can go from an epoxide to this final product, okay, and we'll do all of that too. All right, so then how do I make an epoxide? Okay, so I can make epoxide two different ways. So I can make an epoxide using an alkene, or I can also use halohydrin. So both of these are possible, but I should say or. Okay, so I can use either the halohydrin or I can use an alkene. But the thing about the halohydrin is that for the halohydrin, I will need to make an alkene first. So why increase my steps? Okay, so which means that the alkene is a better choice. Okay, so alkene. Now, how do I get an alkene? I cannot get an alkene from an alkane straight away, all right? That is an elimination reaction, and alkanes don't really do any kind of elimination because they don't have a good leaving group. Leaving group, right there is your key, okay? So which means that I need a leaving group over here. So the only thing I know that works best is, of course, going to be bromine. So because I need the alkene on the 1 and 2 carbons, I can have bromine on either of these two sides, okay, of the alkane. So then which one is easier to make? So this one should be easier to make because this is a more substituted carbon. So these are easier to form than the non-substituted carbons, okay. So how do I make this alkyl halide, this one over here, from an alkane? Now this one I can do because I know that I can use free radical reactions, okay, to do all of this. So this is all a backward synthesis going on, okay, a retrosynthesis. So in the retrosynthesis, let's go ahead and write out our reagents now, okay. So alkane was supposed to be our starting material, so we have that over here, and using that alkane I can use bromine, okay, in presence of light, to give me the alkyl halide that I need. And this is going to be a free radical mechanism. I'm not required to write the free radical mechanism, but I'm just writing it for you, okay, so that you will remember this is what it is. And this is the one that I'm going to form, okay, because when I do bromination, my primary product is going to be the bromine on a more stable carbon. So you can say that you can form more than one product, and that is true, because if you take pentane and you do bromination on that, this is one product you will form. You will also form this, okay, because both of these halides are going to be stable, and this is something we have to live with, okay, in this one. So that's not going to be some issue at this point that you have to worry about, okay, because once you get these two products, you just simply separate out the one that you need and you go on from there, okay. At this point, that's how we are going to focus. Okay, so then the next step is going to be elimination, okay, because now once you have the alkyl halide, now you need to do elimination. So what kind of elimination is this? This is going to be very specifically Hofmann elimination. Why is it Hofmann? Because my alkene is a less stable alkene. So for a Hofmann elimination, I need to have something like an E2 elimination because E2 gives me the Hofmann product. So what are the reagents that I need for Hofmann or E2 is I need a nice, strong, big, bulky base. Okay, so this is going to then give me the less substituted alkene or the Hofmann alkene. All right, so your reagents have to be as specific as you can. So if you want to use methoxide or ethoxide, which is also a good base, you can use those too, but remember to write heat then, okay, with them. So if you write methoxide, that's fine too, but you have to write the heat with it because methoxide is a small base, and if it's a small base it can also do SN2 reaction, okay, but a bulky base will specifically give you E2, okay, because it's too bulky to do substitutions, okay. All right, so now let's go on to the next step where we have the alkene now. So from an alkene we are going to the epoxide, okay. So from alkene to epoxide is a simple one because that is MCPBA, which is the metachloroperbenzoic acid. So that's an easy one to do. And then the last step where you actually have the ring opening going on. So here we know that epoxides, no matter what you use to open the epoxides, you're always going to get the alcohol. Okay, that's always going to be there. So which means that your nucleophile is shown by what is attached over here. And so your nucleophile here is the methoxide. Now, if you want to write sodium methoxide, that would be lovely. If you don't, it doesn't matter. Methoxide is the main thing here. So I know there is a lot of stuff written over here because I'm trying to explain to you how I get to all these things, but this is what we call retrosynthesis. Okay, so let me take you back once more with this. So we're starting from an alkane, and alkane can be halogenated, okay, using bromine to give alkyl halides, and this is a free radical mechanism, okay, nothing else is going to work on an alkane. Then once you have a secondary halide, you can treat that with T-butoxide to give you E2 elimination in order to form the Hofmann alkene. All right, once you have the Hofmann alkene, which is the less stable alkene, it's a terminal alkene, not always a terminal, but the less stable one. In this case, it's terminal, and that you can then use to treat with MCPBA in order to give you an epoxide. So if you were writing the synthesis as straightforward, your arrows will actually be going, and let me use the green color again, it will be going actually this way. Okay, so that's how you would write the straightforward synthesis. But the blue ones right now, okay, the ones that I've circled, these ones are all going to be retrosynthesis. Now, I do like the retrosynthesis because it shows your train of thought. It also keeps you on track, but if you show me the straightforward synthesis, that's fine too. And I'm really sorry this became a little bit messy, okay, but it happens. Okay. And then the last step that I was going to mention over here, from the epoxide, you need to have a nucleophile, okay, in order to open the epoxide. And the nucleophile I need here is the methoxide because that's what I have attached on my product. Okay, so that is how you will do this retrosynthesis.